Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at sections 20.5 and 20.6 of the Brown main book, dealing with free energy and the relationship to cell potential and so forth. Now, one of the things we looked at in class, as well as in the notes, was that as a general redox reaction, if you wanted to calculate the cell potential for any redox reaction, it would be the reduction potential for the reduction process minus the reduction potential for the oxidation process. Now, remember when we looked at this from a voltaic point of view, we talked about this as cathode and anode. And remember, that was just specific to a voltaic cell or a galvanic cell, a spontaneous reaction. But since anodes and cathodes are different when we're dealing with an electrolytic cell, a non-spontaneous situation, a better way to look at this is the reaction that's listed here. So remember the whole cathode minus anode thing that only worked for a voltaic cell. If we're not sure whether it's spontaneous or not, then we use this more general form of that equation that we talked about. Now, as it turns out, if you get a positive value for the cell potential, then you know it was a spontaneous reaction. So that'd be a voltaic cell situation. And if you get a negative value for your cell potential, your EMF, then that would be a non-spontaneous redox reaction, and you'd know you'd have an electrolytic cell situation. So this general form will work really with any redox reaction. So even when you're doing voltaic cells, which we talked about as cathode minus anode, this is really a more general way that applies in all situations. So if you use this for any situation, you'll always get the right answer. And remember, the sign of the cell potential, the sign of the EMF, will tell you whether it's a spontaneous or a non-spontaneous reaction. Now remember, spontaneity is related to an idea from our previous chapter, Gibbs free energy. So we're also going to relate Gibbs free energy to redox reactions. So the delta G for any redox reaction can be found using this equation, where delta G equals negative NFE, where N stands for the number of moles of electrons transferred. So if you've got your balanced redox reaction, remember how we balance electron transfer, that's what we're looking at for the N value. And F is what's called the Faraday constant. Now, there's a box around this because this is something that's given on the AP constant sheet. 1 Faraday equals 96,500 coulombs per mole. So coulombs per mole of electrons, basically. Now, another sometimes more useful form of this is here. This is actually also on the AP constant sheet. So if you look, you'll also find this value there. It talks about the number of electron volts per atom as 96.5 kilojoules per mole. That's that 96.5. So it would be realistically electron volt per atom. So that's hidden, but it is there. And this is a value we end up using in our delta G calculations. So it's really based upon a Faraday, which is 96,500 coulombs per mole. And if we want to deal with energy, we would use the 96.5 kilojoules per volt mole. And E deals with volts, so that's why we'll be using that second one we looked at there. Now, under standard conditions, we put the little knots there, and we would have this equation. And remember, this equation is on the AP constant sheet, so it's not one you have to memorize. You just need to understand what N stands for, what F stands for, and what E naught stands for. Now, to calculate the Gibbs free energy for a reaction, and this is a reaction that we looked at in class. So this is one that we studied how, what the EMF or the cell potential of this would be, and looked at, making a voltaic cell out of this. We would use this equation then for what we looked at with this reaction. Now, remember when we did this in class, the electron transfer was 6 electrons each way. That's why the aluminum had to be doubled and the magnesium had to be tripled in the balancing of that redox reaction. And the cell potential was 0.71 volts for that particular reaction. So we know the N and we know the E naught. And since F is our Faraday's constant, the 96.5 kilojoules per volt mole, if we plug those values in, our answer ends up being negative 410 kilojoules per mole. If we go to 2 sig figs, which the 0.71 volts limits us to 2 sig figs here. So the Gibbs free energy for this reaction is negative 410 kilojoules per mole. Remember, that's a negative value for delta G. Negative values were spontaneous reactions. Remember, we looked at this as a voltaic cell, so it makes sense we should return a negative value for our delta G. Now, we also looked at in previous chapters the relationship between delta G and K. our equilibrium constant? Well, if delta G is related to E, it's also related to K. So we really have three different variables here we have to be able to manipulate between. So back in chapter 19, we talked about this equation, delta G equals delta G naught plus RT ln of Q. So if we have a reversible equilibrium system and we're not at equilibrium, we can actually calculate our non-standard delta G value. Now, if we are at equilibrium, remember Q becomes K and delta G is going to be 0 because at equilibrium, delta G would be 0. We know then that delta G naught would equal negative RT ln of K. So basically putting um, this equation from chapter 19 together with some other ideas, we can end up with this relationship. And since delta G naught is going to also equal negative NFE, we can substitute that in and we end up with this relationship. So if we manipulate that relationship a little bit and solve for E naught then has to equal RT over NF ln of K. And remember, F stands for our Faraday's constant. R is our ideal gas law constant. T would be our Kelvin temperature. And K is our equilibrium constant. So we can use this equation to look at the relationship between E naught and K. So if we know what delta G is, we can calculate E naught. If we know what E naught is, we can calculate delta G. If we know what delta G is, we can calculate K and vice versa. And we can also do the same thing between E naught and the ln of K. Now, if we take that equation and substitute in our constants, remember R and F are constants, we end up with E naught equals 0.0592 over N log of K. So this is basically a simpler form of the previous equation by getting rid of our constants. Now from there, we can isolate the K value. And notice this is boxed. That means this is something that's on the AP constant sheet. And if we want to look at the relationship between K and E naught, K would equal, take the log of both sides, that would K equals 10 to the N times E naught over 0.0592. So between these two equations, we basically have two relationships. If we know E naught, we can solve for K. If we know K, we can solve for E naught. So since delta G is related to K from previous work, and delta G is related to E naught from the previous slides, that means there's also a relationship that we can derive between K and E naught. And remember, this box means that this is a relationship that you can find on the AP constant sheet. So a form of that is on our AP constant sheet. Now, the next section, because 20.5 really dealt with two ideas. Our general calculation for any redox reaction, and then how our cell potential is related to Gibbs free energy, which is related to K. Now in 20.6, we get into looking at situations where we're not at standard conditions. Because remember, when we calculated our cell potential, we were talking about E naught, which meant, we had 1 molar concentrations. Well, if we're not at 1 molar concentrations, how can we then calculate cell potential and so forth? Well, that's where the Nernst equation comes in. So if we want to calculate cell potential EMF under non-standard conditions, then we have this relationship known as the Nernst equation. So we start with the idea that, remember, delta G equals delta G naught plus RT ln of Q. We're using this because, remember, this situation dealt with non-standard calculation of delta G, and that's what we're looking at here under non-standard conditions. If we substitute in what delta G equaled, the negative NFE for our two values, then we end up with this form of the equation. If we divide both sides by negative NF, we end up with an equation that is known as the Nernst equation. So if we want to calculate cell potential under non-standard conditions, that's not an E naught, that's just a plain E, we would need to calculate E naught, so we need to find our standard cell potential, and then we would subtract from that RT over NF ln of Q. And remember, these are constants. We looked at that idea before. So we can reduce that then to this equation. So E would equal E naught minus 2.303 RT over NF or log of Q. So now we've got a way to calculate this because we're under standard conditions. If we've got a reversible reaction and we know our concentrations, because that's what Q is related to, remember, our equilibrium expression is looking at relationships related to concentration. We have a way to plug in for current concentrations and calculate what our new cell potential is. So at room temperature, we got 298 K. If we substitute our R and F into that equation, remember that gives us our 0.0592, that equation then becomes this, which, get rid of the constants and go with a simpler form, is always a much easier expression to use. So now our Nernst equation comes in this form. And remember, that is a form of the equation that we need to be comfortable with because we're going to be using it for these types of calculations. And once again, that box means this is on the AP constant sheet under the oxidation reduction electrochemistry section. So if we want to calculate at anything other than 1 molar concentration for some voltaic cell, this is the type of calculation we would use. We know that under standard conditions, it's our E naught. We can find that using our half cell potential, cathode minus anode. So this value is something we can easily calculate if we know what the reaction is. And from there, we can get our N. And using the concentrations given, we can get our Q, and we can calculate what our new cell potential is. Now, the Nernst equation, which is what you look at here, helps explain why voltage drops as a cell, like a battery discharges. A battery is an example of a voltaic cell. And if you've ever used batteries, you know that in your flashlight it starts out nice and bright, but over time it seems to run downhill a little bit and you're not getting quite as bright. Well, Nernst equation is a way for us to evaluate, what's going to happen to our actual cell potential, which is what we're, that value for our cell potential is what we use to do useful work. Why, when we change from 1 molar concentration, it ends up going down. So when the reactants become products, as our reaction is occurring over time, so the components of our battery are being consumed as the battery is being used, what's going to happen is Q is going to get larger. And if Q is getting greater, and we're subtracting this value from E naught, that means our value for E is going to go down over time. So as our concentrations are dropping and our reactant on our reactant side and becoming products, Q becomes greater and E drops. So as the concentration of product increases, your voltage drops. And as the concentration of the reactants increase, your voltage is going to increase up to a maximum of your E naught. And that brings up kind of a unique situation. There's this thing called a concentration cell where we can literally make a battery where we're dealing with kind of the same reaction but having different concentrations. So notice that the Nernst equation implies that a cell could be created that has the exact same substance at both electrodes if we have a difference in our concentrations. For such a cell, E naught of the cell would be 0, but Q would not be 0. And therefore, as long as the concentrations are different, then E is not going to be 0. So as you see up top here, in this situation where we have different concentrations between the two sides, even though it's the same reaction on both sides, we're going to get a voltage registering here. So we actually created voltage with the exact same chemicals because we have a difference in concentrations on the two sides. And that's known as a concentration cell. And basically what happens is until we reach equilibrium, you're going to end up with a voltage. And when the voltage dies, it's when we've reached equilibrium. So using the Nernst equation, we can actually calculate, based on our concentrations given, what our EMF is going to be. So let's say we've got a reaction between zinc and copper ions. So a situation like zinc being added to copper sulfate. We can calculate the EMF if we're not at standard conditions. Remember, when we did this before with the values from Appendix E, we were dealing with standard conditions. You'd find the cell potential of the reduction cell potential for our reaction happening at the cathode, our reduction reaction. We do the same thing for the reaction happening at the anode, which would be our oxidation reaction. Do cathode minus anode, and we'd calculate what our EMF would be. Well, that's if we're under standard conditions, which imply 1 molarity. Well, let's say we don't have that. Let's say we have 5 molar copper ions, and we end up making 0.05 molar zinc ions are in our solution at the beginning. So for this reaction, if you look at the electron transfer, N is going to equal 2. So basically this is, in the zinc half reaction, it involves 2 electrons. In the copper half reaction, it involves 2 electrons. So our electron transfer here is going to be a situation where N equals 2. Now, E naught for this reaction, because this is one we've calculated before, is 1.10 volts. This is something we looked at in notes earlier. So this is a reaction we've studied before, and we did the calculation before in previous sets of notes. So N equals 2 for this, and our standard cell potential, our E naught, is going to be positive 1.10 volts. So if we plug these into the equation, remember N was 2, our 0.0592 is our constant, and the log of Q, we're going to end up with the concentration of our zinc on top, because remember the Q for this reaction would be the concentration of Zn2 plus over the concentration of Cu2 plus. So that substitutes in like that. Remember, we're just setting up our K expression like we've done all the time. And we end up with this equation. And we can solve for E, and we end up with 1.16 volts. We're actually higher than standard conditions because we've got such concentrated molarity of our copper ions. So in this particular case, the actual voltage we will read under these conditions would be 1.16 volts, not 1.10 volts. And now remember, as time goes by, and our copper is being converted into, or I should say our copper ions are being converted into solid copper, what's going to slowly happen over time is this value is going to start to drop. And eventually it's going to be at the situation where we're 1 molar of each and we would equal 1.10. And as the reaction keeps progressing, it's going to start to go down from there. And that's what happens as we use up our battery. And that ends our notes over section 20.5 and 20.6.